Okay, so welcome to this sixth lecture in fluid mechanics or viscous flow. Today we will very briefly summarize the two Stokes problems that we looked at during the last lecture. So Stokes first and Stokes second problem, and then we will very quickly go to boundary layers, which will then be the main topic for the next two lectures before we will go further to stability. So if we start with boundary layers, if we start with the Stokes problems first, so these were the two things that we looked at: Stokes' first problem and Stokes' second problem. Stokes' first problem is a very simple kind of time-dependent solution of Navier-Stokes, where the idea is that we have a flat plate which we start to move at time zero from rest to move with a constant speed v to the positive x direction. And then, of course, the result that you would expect is looks something like this. So u divided by this v velocity as a function of y and time will kind of look like this. So first we will have a very sharp increase or decrease of the velocity. And then via the action of the viscosity, we will kind of push this velocity profile more away from the wall. You would increase the speed of the fluid close to the wall more and more, up to the point that at time infinity, so after a long time, you essentially would have accelerated all the fluid in the domain. So your velocity profile will become vertical. Now, the way that we solved this, and that's kind of the main aspect here, the way that we solved it was with the help of a similarity solution. So what we did is we found a similarity transform that combined the vertical coordinate y and the time coordinate t into one variable, this variable eta, which I haven't written down here on this summary slide, but we combined it into a new variable eta, the similarity variable, and then we could transform the governing partial differential equation into an ordinary differential equation, then written in terms of this eta, and then we could solve this ordinary differential equation in a much easier way. So the whole idea of Stokes' first problem is a way to highlight the power of similarity solutions when we combine different coordinates, in this case y and t, into one new coordinate, which then transforms our partial differential equation into an ordinary differential equation. So this was Stokes' first problem. Then we also looked at Stokes' second problem, which is also an illustration of one particular way of providing a solution to an unsteady partial differential equation. The problem is as follows, that you have again a flat plate, but as opposed to Stokes' first problem where you just accelerate this plate, in this case, the plate is moving back and forth. Then the idea or the question is, how does this wall movement transpire into the fluid domain? And this we could solve via going into complex space, because we know that this oscillation is a harmonic function. So we actually made an ansatz of our solution in complex space with a harmonic function, with a complex kind of rotation in complex space. And with this, again, we could transform the partial differential equation into an ordinary differential equation, which we could then solve by separation of variables. And the result is given here. And interestingly enough, this result here is composed of essentially two parts. One part is a damping of the oscillation as a function of y. So you see this here in this diagram that we also plotted last time, where you see that the amplitudes of this oscillation decreases as a function of y. And then we also have a propagating wave in y and t. So essentially this maximum here would kind of propagate away from the wall into the domain with a specific wavelength or period, 2 pi divided by k, and this k was something that we could derive last time. So that means the interesting thing here is that we have two different parts of the solution which are combined with a multiplication. And again, this we could obtain by going to complex space. So these two problems, Stokes' first and Stokes' second problem, perhaps as such are not so relevant. Maybe they are, but maybe they're not so relevant as a solution per se, but they show how you can actually obtain these solutions. And the methods, both the similarity and also the one going to complex space, are ways that we will use later on in the course, a little bit more on how to compute exact solutions. Now, before I go further, I actually forgot last time to ask you one poll during class, so I would like to do that now. It's actually related to Stokes' second problem, and the question is kind of perhaps an easy question, I don't know, but the question is, what is the effect of viscosity in Stokes' second problem? Remember, we talked about that a little bit last time, but now I would like to ask this question explicitly. So in Stokes' second problem, what is really the effect of viscosity? And there's a few options that we can look at: momentum diffusion, smoothing of the velocity profile, dissipation, dissipation of mechanical energy, dissipation of energy in general, slowing down the plate, or change of frequency. So what do you think? What is the effect of viscosity? Okay, so I see that is answers coming in. We will afterwards go through all the answers and discuss whether or not they actually make sense or make no sense for this particular question. So it's a multiple choice question in the sense that you can actually choose multiple solutions here. So it's not just one, at least I hope it's in that way.
No, actually we can only choose one option.
Oh, you can only choose one. Okay. Then, okay, sorry. I thought I changed the settings, but then maybe it didn't work. Okay. Which of course gave away already one part of my answer. It's actually not just one thing that is correct, but some of them are more important than others. Okay, I'm sorry about that. Okay, but let's go through the answers that you have. So what is the effect of viscosity in Stokes' second problem? Well, most of you answered it's momentum diffusion. So we have a moving wall, which of course induces momentum into the flow, and somehow this momentum needs to go up. And of course, this is correct. Without viscosity, you know, the wall would just move back and forth and nothing would happen in the flow. So the foremost duty or effect of viscosity is, of course, that the different layers of fluid, they talk to each other and they diffuse the momentum or transport the momentum from the wall further away. So this is certainly the most important point. Second possibility was smoothing of the velocity profile. Well, I mean, of course, that happens to some extent, but in this case, it's actually not so important because we only excite the flow with one wave number. So that means there's actually not much smoothing that needs to go on. It would be different if the waveform was much more, you know, the waveform of the movement would have higher frequency in it, higher frequency, so it would stop and start and, you know, have, you know, shocks and so on. And then you would see this smoothing of the velocity profile. In this case, this is actually not the relevant part. Next option, dissipation of mechanical energy. Well, you see that the amplitude here is actually decreasing. So there is a certain dissipation that happens here. And the dissipation, of course, is proportional to this e to the minus ky. So we lose energy, mechanical energy, when we go higher up. And of course, this is dissipated from motion into the temperature field. So yes, there is dissipation of mechanical energy. Dissipation of energy, however, that is not the case. I mean, we just dissipate mechanical energy into temperature or some other form, but the energy as such, including the thermal energy, is of course constant. Slowing down of the plate, nobody said that, or nobody answered that. That's of course also not the case, because we actually impose that. What happens, of course, is that the viscosity creates a certain resistance for us to move the plate, and that resistance is probably higher the higher the viscosity is, but it would actually not slow down the plate. It would just create a larger drag force that we have. And then the last possibility, change of frequency. Well, of course, now I need to discuss what I mean with frequency. Here, in fact, I meant the L, the spatial frequency, or the wavelength of this oscillation, and that is of course dependent on the viscosity, because that's 2 pi over k. Of course, here we have a viscosity in. So the higher the viscosity, or so the wavelength here really depends on the frequency that you the wavelength L depends on the viscosity that you have. So it means that the higher the frequency, the higher the viscosity is, the higher the wavelength is. Okay, so with this, I would like to close the topic of the 2 Stokes problems, and I would like to continue with the next topic, which is about boundary layers. Just take away this yellow stuff. Right. Okay. I would like to start with the topic of boundary layers. And of course, this is an extremely relevant problem, because boundary layers is really that part of fluid mechanics where engineering meets fluid mechanics, because that's where bodies of various types actually start to interact with the surrounding fluids. So, boundary layer theory. So in that sense, this is one of the most important topics within engineering fluid mechanics. We will now talk about the basics. With basics, I mean we talk about the derivation of the laminar boundary layers, the similarity solutions, the basic concepts of boundary layer thickness, and so on. And then later on in this course, with me in a few hours, we will also talk about the stability of boundary layers. But then later with Ramis, you will also talk about turbulent boundary layers. So meaning what happens if these boundary layers become turbulent, and what kind of velocity profiles, what type of friction you will get under these circumstances. So what is the basic idea of a boundary layer, or what is it? What is it actually when we talk about a boundary layer? So the presence of a wall in a flow domain, and with a wall I mean a region or a boundary where I have no slip boundary conditions, which means that the velocity is actually 0. So the presence of a wall is only felt by the flow in a thin region close to this wall. So that's the basic idea of a boundary layer. Now, let me illustrate what I mean with that. If I have here an airfoil, let's say, I have a free stream. So I have a velocity coming like this that approaches this airfoil. And of course, I have the streamlines kind of going like this around it. And now the idea is that the actual effect of the boundary layer is only felt in a small region close to this wall. The region further away from the wall, from this body, of course, still feels the presence of the object by having these deflecting streamlines, but it will not feel the direct viscous effect of the wall. So it would not slow down its velocity to meet the no slip boundary conditions. just because of viscosity. You will feel the general displacement effect, but not the immediate viscous effects. And this boundary layer here, that's the red thing, this would be a boundary layer. And this boundary layer would have a certain thickness, which we can say that this thickness is typically called delta. Of course, this delta is much smaller than, let's say, the global scale of this wing, which could be described with a capital L. So the whole idea of a boundary layer is that we have a thin layer adjacent to the wall, which is very thin compared to the global dimensions of the flow. So this red thing, this is the boundary layer. And it's that region where viscous effects, so the effect of viscosity, which then also ultimately leads to the no-slip boundary condition, which is, as you know, is due to viscosity. So in this boundary layer, it's where viscous effects are relevant. In the rest of the domain, this is actually quite well described with an inviscid approximation. So we can say this could be where we have potential flow, if you now think of an irrotational flow, or it could also be done with the Euler equations. So the whole idea that now, of course, you may think that this is a very simple idea, but actually it was quite a mental struggle to come to this conclusion that there is only a thin boundary layer where viscosity is important. And it was not at all accepted with welcoming arms of the scientific community. It goes back to the work by one of the pioneering figures in fluid mechanics. It goes back to Ludwig Prandtl, and I guess you have heard his name before from also the part by Alessandro Talamelli, when he also talked about the Prandtl equations or boundary layer approximations. So Ludwig Prandtl, who lived 1875 up to 1953, so roughly 100 years ago, he was actually presenting this concept in a paper in 1904, so not so long time ago. And as I said, it was not fully clear in the beginning that this is really the right approach. Very quickly, people have, of course, realized that this is exactly what happens in reality, and it also turned out to be a useful tool for engineering design, because it really meant that there's a theoretical basis of also being able to ignore the effect of viscosity further away from the wall. Anyway, so this is the basic idea of a boundary layer. Now, of course, we also now we need to start to be a little bit more precise. Okay, we say we have this thin region with this delta, but why do we actually have a thin region of delta? So, physically speaking, what is really happening? Well, I guess now we can use all the tools that we have already started to get acquainted with in the Stokes first and second problem. Essentially, it means that the information from the wall, and in this case, with information, I mean essentially the no-slip boundary condition. So the information from the wall diffuses into the domain, and it does that with a certain diffusion constant. And this diffusion constant obviously is the viscosity eta. So that means that the information that, here I have a no-slip boundary condition, so I need to slow down the flow to be zero. This is an information that kind of diffuses away with this constant eta. So at the same time, so while we have this diffusion going on outwards, at the same time, we also have that the fluid convects. And I should write that you can read it. Convects downstream, convex downstream with a specific speed, let's say u infinity. So now let me try to explain what I mean with that. So we have the free stream, now I call it u infinity. So we have, in this boundary layer here, we have the convection, the diffusion with a diffusion constant eta outwards, but at the same time, we have the flow moving downstream with a certain speed. And of course, that means that I convect out, but at the same time, I'm moving downstream. So that means that the information is not going just vertical, but it kind of goes along the shape of this body. And of course, that means in consequence that we have the thin boundary layer that actually starts very, very thin here on the front, but then as we go downstream, it becomes thicker and thicker because of this interaction of convection and diffusion out. And actually, this idea that you have a boundary layer that is growing downstream, that is a very relevant aspect of boundary layers. And this is already my first question that I would actually like to ask you. I will ask again. I guess I need to close this poll first, but now I have a second poll that I would like you to answer. So if you assume that we have this boundary layer on this wing, let's say, how fast do you think is this boundary layer growing if we go from the front to the end? Is it growing linearly with distance? Is it growing as a square root with distance? Is it growing inverse with distance or inverse with a square root? The reason why I'm asking this is that it's quite an important knowledge to have when it comes to laminar boundary layers, because it's always the same. It's always the same type of growth. And it very quickly allows you to assess how thick such a boundary layer actually becomes. And also what happens if you make the body, let's say, twice as long, whether it doubles or not. Okay, I see now the answers. And most of you say it grows as a square root with distance. So that means if I make the body 4 times longer, it only grows by a factor of 2, let's say. Let's see how we can calculate this. Now, so the question was, how fast does the boundary layer actually grow? Now, most of you said as a square root, but I guess we're scientists, so we would like to actually know exactly how this is being done. Well, I said before that the growth has to do with the fact that we have the convection in the streamwise direction and the diffusion in the vertical direction. So what we can do here, very simply, is a dimensional analysis. And what we do is we actually estimate the typical time scale for the diffusion in the vertical direction. So a typical time for the vertical diffusion. Well, that's actually, how do we do that? Well, we know that diffusion, so if you just think of a diffusion equation, it will be something, so if you have the diffusion equation, du dt is something like nu times d squared u dx squared. So this would be some type of diffusion equation. So that means that in the diffusion we will somehow have a velocity and a length, but the length here is in is a square, and then we have a viscosity. So if you now try to form a velocity or a time scale rather, we would actually get something like this. Delta t, the diffusive time scale, would be proportional to the delta squared, so this is x squared, divided by the viscosity. So this is the time scale that we can build with the viscosity and length scale. So this is what we can get from a dimensional analysis. At the same time, if we now have a time scale for the vertical diffusion, we can also build a typical time scale for the convection. This is actually a bit simpler because there we just know, okay, the time scale essentially is proportional to a length divided by the viscosity, L divided by U infinity. This would be a time scale related to convection. Now, of course, we can say, now to come to our conclusion, we can say that these two time scales, they actually need to be the same in order to find out how the boundary layer growth would look like. So that means we can essentially set this delta squared divided by nu should be more or less of the same order as L divided by U infinity. And of course, now we can start to modify this expression a little bit. So we can compare the two length scales. So this delta, which is the small one, with the L, which is the large one. So delta squared divided by L squared, which then becomes proportional to nu divided by U infinity times L. So that's just kind of reordering these expressions. And now, of course, we see that this one here, this expression, actually resembles a Reynolds number, which we can now call a Reynolds L. So it's the Reynolds number based on the free stream velocity and the length of our obstacle. So that means if we are now interested in just the thickness of our boundary layer, so delta divided by L, this is something that is proportional to the Reynolds number, Reynolds L, to the power of -1/2. And of course, this is a very interesting result because now we know that the thickness of my boundary layer in relation to the global dimensions is something that grows as a function of Reynolds to the -1/2. And this is valid for delta divided by L being much, much smaller than 1. And of course, that means that Reynolds is much, much larger than 1. So for in the high Reynolds number limit. So this would be the kind of the important scaling that we have now found just based on dimensional analysis. Okay, we have still not answered really our question from the beginning, how fast the boundary layer would grow as a function of downstream distance, but this we can now do based on this. So my delta as a function of L would then be essentially L times the Reynolds L to the -1/2. Of course, that just becomes L times the square root of nu divided by U infinity times L. Now we can change this a little bit. That gives you nu divided by U infinity times the square times L. And of course, that becomes then C times the square root of L. So that means if I increase my length with a factor of 2, or with a factor of 4 rather, then delta would grow by the factor of the square root of this length, so by a factor of 2. And of course, that means exactly that the boundary layer thickness along a body grows as the square root of the length. And this is really a general result that is always the case for a laminar boundary layer. The growth is the square root of the length. And in the end, it really comes from the fact at the very end, it really comes from kind of this second derivative that we have in the diffusion. That is the reason why convection is more dominant than diffusion, and therefore it's not growing linearly, it's only growing as a square root. As soon as you have a turbulent boundary layer, of course, then the situation is a little bit different, because you not only have the viscous diffusion, but you also have what is called a turbulent diffusion. So you actually grow faster because your diffusion is enhanced by turbulent motions. But this is something that Ramis will tell you more later on. Okay, so now that we have understood kind of this basic idea of how a boundary layer is growing, then we should now go back to starting to do some kind of more serious calculations. So what we always do in boundary layers, or the basic assumption in boundary layers, now based on exactly this result that we have just obtained, namely that the thickness in Y is much, much smaller than the kind of the development length in X. We always do this assumption that not like this, that the changes in Y, so d dy, that these changes are much faster than the changes in X, because it's much thinner in Y as compared to the length. So that means that the changes in Y are much larger than the changes in X. And of course, this is something that you have talked with Alessandro about. This is what is called the Prandtl hypothesis. And this is really the underlying assumption of boundary layers. This changes the mathematical type of the equations from essentially hyperbolic to parabolic. So this is really the crucial aspects of boundary layers. If you now just draw a two-dimensional and steady boundary layer profile, in the simplest case, so as a function of Y and X, if you assume now that this is a flat plate, so a solid surface which has a leading edge here at 0, a leading edge, then we have a boundary layer that kind of starts here at 0, and then it grows as this square root that we have just introduced, or that we have just found. So this delta, the boundary layer thickness, would be proportional to the square root of the coordinate x. And inside the boundary layer, so if I'm just trying to plot now a profile at maybe this position, kind of means that outside the boundary layer, so everything that is above this point here, I would have a uniform velocity profile. If I had a uniform velocity profile here in the beginning, this was u infinity, then I would also have u infinity here. And inside the boundary layer, I would now feel the effect of viscosity. So that means I smoothly need to connect from the no-slip boundary condition at the wall to the undisturbed free stream further away. So all the velocity gradients, they are essentially confined to this region inside the boundary layer. That's exactly the basic idea, or the basic idea. That's exactly the idea of a boundary layer. Now, I just want to mention one additional thing, which will become important. Now, I have mentioned that here this is u infinity everywhere as a constant, but actually this can also be an edge velocity, which is a function of, as an edge velocity, which is a function of x. So it could be ue as a function of x, and then of course I could also have a pressure distribution in the free stream, which is a function of x as well. So that both of it is possible, and even a varying free stream velocity will lead eventually to a growing boundary layer with a growth rate which is proportional to delta x, to a square root of x. So it's essentially, so what is going to concern us now during the next few hours is to calculate this velocity profile inside the boundary layer as a function of the various properties, the edge velocity, thickness, viscosity, etc. Before we do that, I would actually like to spend a few minutes on one of the kind of the most fundamental integral concept of a boundary layer. And that is the concept of a boundary layer thickness. And we have already talked about that when we mentioned Stokes' first and second problem. And at the time, we introduced one option or one variant of defining the boundary layer thickness. So we can say, as before, the way we did it was just to say, okay, we take the velocity as a function of y, and we define this y to be delta, the boundary layer thickness, if the normalized velocity, so u divided by the u edge at this particular position, corresponds to some value, let's say 99 or 0.99 or 99%. And this is then what we will call the 99% boundary layer thickness. So we just look for that point when we have reached kind of 99% of the free stream velocity, and this point would then be the boundary layer thickness. And this obviously is called delta 99. And if you're a little bit into fluid mechanics, people all the time talk about delta 99. This is kind of the implicit meaning. It's that position where the velocity has reached 99% of the free stream velocity. It's not just 99%. Sometimes people take the 95% boundary layer thickness, or when you have a lot of fluctuations, they even take the 90% boundary layer thickness. Or as we have done for the case with the Stokes first problem, we actually have talked about the 1% boundary layer thickness. So when the velocity has decayed to 1% of the free stream or of the wall velocity. So this is the first way of estimating the boundary layer thickness. And of course, this is something that is very easy to measure. This is very easy to measure. It's also easy to interpret. I mean, I told you now what delta 99 means, and I guess all of you would now completely understand what it means. But of course, and I think that's really the main aspect here, why we also want to have other ways of measuring the boundary layer thickness. It actually is, but it is quite, I would say, ad hoc. I mean, why do I take 99? I can take 99.5. I can take 95%. I mean, there's no real physics in it. There's no real meaning apart from just looking at the shape of the velocity profile. But of course, it's a very useful thing for us to kind of understand what a boundary layer thickness is. So this is the first option, delta 99. But as I said, we need to have some other measures, and I guess there's two other ways of estimating the boundary layer thickness, which I would like to introduce now to you. First one, which is probably the most useful one, also when it comes to kind of physical interpretation, this is what is called the displacement thickness. And that is something that's called delta star. That's just a kind of notational, or people have started to use that notation, delta star. Sometimes it's also called delta 1. The idea with the displacement thickness, I guess the name already says it, is to estimate actually the displacement by the boundary layer. The idea is to estimate the added thickness of the plate due to the growing boundary layer. So what do I mean with that? So what is the idea of estimating this added thickness? Well, actually, there's quite a straightforward physical explanation, which I think is quite instructive for you to understand. So if I'm again plotting just a typical boundary layer profile, I have a wall here. I have my boundary layer profile. I'm kind of drawing it here in red. Probably looks like this. So this would be my edge velocity. Of course, my 99% boundary layer thickness would be somewhere here. So this is my velocity. Now, how could I estimate the added displacement of this boundary layer profile? Well, the idea could then be, okay, what would happen if I would just continue this profile straight, so without change, up to a specific point, then go to 0. Then I could say that actually this point, this thickness would correspond to my added thickness, so kind of the apparent thickness of my body if I had this body in an inviscid flow, so flow without viscosity. So that would then be the thickness that an inviscid flow would experience if kind of this area would be the same as this area. So I would essentially move everything that is close to the wall, so this part out here, and then this would be the apparent displacement that I, as a inviscid flow, would feel. And then this thickness here, I could call delta star, my displacement thickness. Now, of course, you can go in and figure out what this actually means in terms of an equation, and you can come up with the fact that delta star would then become the integral from 0 to infinity of 1 minus u divided by ue times dy. So essentially, this is the definition. What it means in practice, now just trying to understand what this integral means. This integral is essentially this area here. So that's what I'm integrating here. And of course, now you can see that it means that I would essentially calculate the thickness of this block close to the wall, which is exactly this positioning of this outer bit into the region closer to the wall. So that gives you then the definition of delta star. With this, I would also like to stop for the first hour, and I take a short break, and then we will continue after the break with 1 second definition of a boundary layer thickness. So let me